Hi AP Calculus students, how you doing today? Section 3.4, this is the second derivative test. So from the first derivative test, what you found was that helped us find on functions where the function was increasing, decreasing, where there was relative max and mins. We did that by first dividing the interval of the domain of the function using discontinuities and critical points. So today when we use the second derivative test, what we're going to be looking at is, I'll come on this side because you're probably writing some notes, is, okay, functions increase and decrease, but they do that in different ways, right? They do that constantly, like in a line, they can increase or decrease. They could do that like in an exponential form increase, right? Or they could do that where they're increasing in more of a, where they're increasing, but the increasing is slowing, is what I'm trying to say. There we go. So what, and that is the second derivative. The second derivative tells us how a function is increasing or decreasing, and that's an important part of a function and about how real world situations change. You know, if interest rates are going up, are they doing that exponentially? Or are they increasing but slowing? Or are they going up constantly? So what happens is then we're going to use a chart for second derivatives, just like we did for first derivatives, but we're going to be finding how the functions are increasing and decreasing. And we're going to be looking at points in between there. Those won't be maximums or minimums. Those will be called inflection points. So the idea is the same. We're just using the second derivative. Then in section 3.6, we'll bring that together. If a function is increasing, meaning its first derivative is positive, how is it increasing? Meaning we're going to look at the second derivative, right? Again, another thought is, what is the second derivative? Well, that's the derivative of the first derivative. And the first derivative is the slope of a tangent line. So the second derivative must be how those slopes are changing. Okay, so we have done this a couple times, looked at these four pictures, but we're going to refresh our memory and do that today. So we're going to provide the sign positive or negative of the first derivative and the second derivative. Okay, so notice in the first picture here, obviously this is increasing, right? Because if I drew these tangent lines here, right, they are all positive. So the first derivative is positive. Notice that these tangent lines are becoming more positive. So we're going to say that because the first derivative is increasing, we're going to call the second derivative positive. Right before we kind of refer that is to velocity and acceleration, right? We're going to leave the concavity blank for a second. Let's go to the next picture. When you draw little tangent lines, they all have a positive slope. So our first derivative is positive, but these slopes are becoming less positive. So we're going to call that a second derivative is negative. When we come to this graph here, notice that these tangent lines have slopes that are all negative. So there's our first derivative. Notice though, as we go to the right, they're becoming less negative. We're going to call that positive. In our last picture, notice again that the slopes are negative and they are becoming more negative. So what I really want to point out to you though, is take a look when this picture, right, is concave up, right? The curve goes up. So we call this concave up, you know, kind of like a smile, right? Someone's up, right? Concave up. And this picture also is concave up, right? Right, like a smile. Though this one is increasing and this is decreasing, they are both concave up. Notice that the second derivatives are positive. So when your second derivative is positive, that is concave up. Notice in the second picture that this is concave down, kind of like a frown, right? When someone's down, they frown. Right, second picture, and also in the fourth picture, this is concave down, kind of like a frown. again, notice this is increasing and this is decreasing, but they are both concave down. So concavity doesn't have anything to do with increasing or decreasing. It's just based on the shape. So notice when the second derivative is negative, that we have concave down. Now, what I want to show you next is what happens, just like when functions are increasing and decreasing, they have relative max and mins. What happens when concavity changes in between there? Let's take a look. Often when you see a second derivative sign changes from positive to negative, in other words, from concave up to concave down, or negative to positive, concave down to concave up, you'll find inflection points. And we call those IPs so that we don't have to keep writing inflection points. So here's a function that you're used to, f of x equals x cubed. Notice here on the left that this is a concave down shape, right? The concavity would be negative. Notice that after 0, 0, that this function is concave up, right? That's definitely a concave up shape. Right here at 0, 0, we call that an inflection point where the concavity changes. So the inflection point would be at 0, 0. Notice we also have inflection points in the sine function and cosine function. So all I did was draw sine from 0 to 2 pi. Notice that from 0 to pi, that the function is concave down, right, negative. Notice from pi to 2 pi, the function is concave up or positive. There's an inflection point right at pi where the concavity changes. So let's actually look at the definition here. The definition of concavity, and again, I usually write that as CV, right? C is continuous, so we use CV, right? And I usually just use an up arrow or a down arrow, concave up, concave down. So the definition of concavity is F is differentiable. Of course, it has to be, right? This is second derivatives we're talking about. And if the first derivative is increasing, right? So if the first derivative is increasing, right? They're talking about how this slope is changing. That's a second derivative. Then you have concave up, right? If the first derivative is decreasing, notice they're talking about how this slope is changing. That's a second derivative. Then we have concave down. An IP, if it exists, will occur at the critical point of the second derivative, where the second derivative is 0 or undefined, right? So again, this goes back to the first derivative, critical points were maximums and minimums, where the first derivative was 0 or undefined. So this works out really well, that a critical point of a second derivative we call an inflection point, and it will occur where the second derivative is 0 or undefined. So you can see the similarities, okay? The actual point must exist. For you to name an inflection point, it has to exist, just like the max or min did. And the concavity must change sign from the left to the right of that critical point, right? It has to change from positive to negative or negative to positive again. That was like relative max and mins. At critical points where the derivative is 0 or undefined, it was only possible there was a max or min. We had to check for a sign change on each side, left and right of that point. And for a second derivative, to confirm that we have an inflection point at a critical point, the concavity, the second derivative has to change sign on the left and the right. And what we're going to do is use a second derivative chart. Same thing, intervals, right? We're going to look for discontinuities and critical points of the second derivative. We're going to find test values in those intervals. We're going to check the second derivative to see if it's positive or negative, so we can say something about the concavity and the inflection points. In section 3.6, we pull the first derivative and the second derivative together. What happened to section 3.5? We already did it. Remember, that was limits at infinity. We did that with chapter 1, Okay. There's also an example video for 3.4 you need to watch. These are the examples I'm going to be doing, 7, 24, 36, and 68. So when you're done watching this, please also watch the examples video. Have a great day.